Let us talk about recursive binary search. We are given a sorted array and an element to be searched in the array. We need to write a recursive function that takes this sorted array as an argument, this element as an argument, and returns index of this element if it is present in the array and -1 otherwise. If there are multiple occurrences of this element, then this function can return any of the indexes. So in this example, 20 is present at index 1, so our output is 1. In this example, 30 is present at index 2, so our output is 2. In this example, 10 is present at index 0, so our output is 0. Let's see these examples. 15 is not present at all, so our output is -1. 5 is not present, so our output is -1. 20 is not present, so our output is -1. Now please pause this video and try to write down a recursive function that takes this array and the element as arguments and returns index if it is present and -1 if not present. Let us do a quick recap of binary search. In binary search, we search an element in a sorted array, and to search the element, we go to the middle of the array. We compare the middle element of array with the element to be searched. If they are same, then we stop our search. If middle element is greater, then we go to the left half. And if middle element is smaller, then we go to the right half. So we have three cases in binary search. We have talked about an iterative solution. Now please pause this video and try to write down complete code for this function. This function should search element x in the array from indexes low to high. It's a recursive function. We are going to change low and high in the recursive calls. I have written here partial code that simply follows these steps. We first compute the mid, then we compare array mid and x. If they are same, we return mid. If array mid is greater, we go to the left half by changing high to mid -1, making a recursive call. If array mid is smaller than x, then we go to the right half. We change low to mid +1 and we keep high as it is. So that's all. We have two recursive calls. Now what should be our base case? When should we stop making recursive calls? We stop making recursive calls when low becomes greater than high, like we did in iterative solution. In iterative solution, we were continuing with these steps of computing mid and then comparing array and mid while low was smaller than or equal to high. The same thing we are going to follow in this recursive solution. We'll do these things while or if low is smaller than or equal to high. We'll stop doing these things when low becomes greater than high. So we can write a base case. If low is greater than high, if we have reached such a condition, then what were we doing in the iterative solution? We were returning -1. So we'll do return -1 here as well. In the iterative solution, we were returning -1 when we were coming out of the loop. Here also, we'll return -1 when low is greater than high. Let's now see the working of this code with this example. We call binary search with low as 0 and high as 6. And we pass the element to be searched as 20. Now what happens in this code? As a first step, we check if low is greater than high, which is not true because low is 0 and high is 6. Now we compute mid, and mid is 0 plus 6 by 2, which is 3. So we execute this line. Now we check which case we are in. Is array mid equal to x? No. Is array mid greater than x? Yes. So what we do? We make a recursive call for array low mid -1. And mid is 3, so we pass our high as 2. We assign high equal to mid -1 when array mid is greater than x. Now when we make this recursive call, our execution again begins from this line, right? And this time again low is smaller than high, so it's fine. We compute the mid, low plus high by 2, 0 plus 2 by 2, 1. And now we compare array mid and x. And array mid and x, they are same. So we return mid at this point. So we return 1. So this function returns 1 to its parent call, right? And parent call, upon receiving 1, receives 1 to its caller. So that's how you get the correct index in this particular example. Let's now see the working of this code for this example. Here we have changed x to 25. So we begin our execution with low as 0 and high as 6. We compute the mid, right? We come here, we compute the mid. We compute the mid as 0 plus 6 by 2, 3. We compare this 40 and 25 and we notice that 40 is greater than 25. So we need to go to the left half. To go to the left half, we change high equal to mid minus 1. So we make a recursive call with high as 3 minus 1, 2. Now this function is stopped and this recursive call starts and again begins the execution from this line. So low is 0 and high is 2, and low is smaller than or equal to high, so we do not fall into this base case. We compute mid, and mid comes out to be 0 plus 2 by 2, 1. We compare array mid and next. We compare 20 and 25, and 25 is greater than 20. So what are we going to do? When 25 is greater, we are going to go to the right side. To go to the right side, we change our low to 1 plus 1, 2. So this is our next recursive call, and it's going to begin its execution from here again. We still have low equal to high, not greater than high. So we are not going to fall into this base case. We are going to compute the mid as 2 plus 2 by 2, which is 2. Now we compare array mid and next. We compare 30 and 25. And 25 is smaller than 30. So we need to go to the left side. To go to the left side, we change our high to mid minus 1. So our high becomes 2 minus 1, 1. Now when you call this function with low as 2 and high as 1, what happens? Your low is greater than high. So you fall into this base case and you return minus 1. So this function returns minus 1 to its parent, and this parent was waiting for this function to call, right? It was waiting inside this condition for this function to finish. And it has finished, so it's going to return its return value. So it's going to return minus 1 to its parent, and its parent was also waiting for this function to finish. So it returns minus 1 to its parent, and its parent also returns minus 1 to its parent. So finally, our binary search function returns minus 1 for this input. So we have talked about recursive binary search. Let's do a quick comparison of iterative and recursive binary searches. Time complexity of iterative binary search is log n. We are going to have order of log n iterations in the iterative binary search. How many recursive calls we will have in the recursive binary search? It is again going to be order of log n. We can prove it using the same logic. We either go to the left half, right half, and if we draw the tree and we see all the execution paths, we can notice that we will have at most big O of log n recursive calls. So time complexity wise, iterative and recursive are same. Let's now talk about auxiliary space. Iterative solution requires big O of one auxiliary space because we were using some constant number of variables. We were not using any array or anything. But in recursive binary search, we need some extra space for recursive function calls. Like when you make this recursive binary search call, this function call stops at this point and it's stored in the function call stack, right? And then this function call is made and this function call stops at this point and waits for this child call to finish. So we have two functions in the function call stack when this function is called, and this function is also stored in the function call stack, and then this function is called. So there would be a moment where we will have 4 function calls in the function call stack. In general, when you have n sized array, how many recursive calls you will have? You will have big O of log n recursive calls. So how many elements you will have in the recursion call stack? Big O of log n. So auxiliary space required for recursive binary search is big O of log n. So we can see that iterative is definitely better than recursive binary search. Iterative does not involve extra function call overhead, requires big O of one extra space. Recursive function requires extra overhead for the recursive function calls and requires big O of log n extra space.